Okay, can everybody hear me? Or somebody tell me if you can hear me.
Yes.
Okay, good. All right, so today I wanted to just kind of go through the homework that I set up, and let's see. So Monday's a holiday. Monday's Martin Luther King Day, so I put down that the homework's due on Sunday night, but which I think that's what I want to try to do so that I can go through it on Monday. You know, go through the answers on Monday, but this time maybe Tuesday night, you know, because there's a holiday on Monday. So anyway, so I wrote a little program that got random pairings of two people, like of grad students and of the undergrad. Since there's 4 courses, I can't do this on Canvas, whatever that thing is that we're using. So anyway, I have like the names, and then there's group numbers here. It's like for the first group, like Josh and Sarah would be like a paired group. The next week, Josh would go with Mike. In the third week, there'd be 3 people in this group. So since there's 7, there's going to be one group that has 3. So it'd be like Josh, Sharon, and Nudeep, right? So, and the same for the undergrads. So I get set up like that. So what I did was I made a program that these are just random arrangement, but it turns out that isn't exactly, sometimes you end up with too many times with the same partner. So look at yourself in here if you want, and then tell me if the problem, like you're getting too much paired with the same person. I tried to go in, at least for the first person, and then like make sure that they didn't always have the same partner. Because if you do it random, like Josh would have paired up with Sarah like five or 6 times, and should only have been like 3 or 4, or maybe 3. You know, there's still 7, so you're bound to be paired with the same person at least 2 or 3 times. Anyway, I didn't go through for everybody, and maybe it's not possible to make it evenly distributed, you know. But anyway, this is kind of close to random. I did go in and manipulate a little bit to try to get it so you didn't so much repeat. I mean, if it's random, you get these repeats in it. That's kind of the point. That's a pretty neat logo, the bongo thing. Anyway, so this is set up for the group, so hopefully that'll be okay. So like 2 of you will turn in 1 homework. Then how to turn it in, since there's 4 different classes, we can't really turn it in. I want a PDF for the homework, and then I guess at least for now, you're gonna have to just email it to my UC email account, like the let's see, what is this thing? It took a while to get this random pairing thing going, but Canvas does that for you. So anyway, my emails, send it to the UC email. This email, okay, and so like Tuesday, like, I mean, the earlier you turn it in, the better. I can look at it, but basically Tuesday at midnight, say. Okay, and then, but next it'll be like Sunday at midnight, you know, Sunday night at midnight. So you have to do it either Friday afternoon, Saturday, Sunday. So you don't have exactly a week to, you know, you just have a few days to do it. Anyway, all these things we'll have to sort out how to do it properly. But for this time, say Tuesday at midnight. Anyway, so the way this is going to work, that they're all down here. So I call it a homework now instead of quiz, instead of homework. And then you kind of look at this one. Someone wanted to go through it a little bit, but so there's 3 papers. Usually there'll just be 1 paper, but this is 1 subject. So the subject is polymer lamellar crystals, and how you get the so the lamellar crystals. See, I'm recording, right? I'll make sure that this thing is recording.
Are you trying to share your screen too?
Oh, shoot. Yeah, I'm trying to share my screen. Thanks. Okay, now it's sharing screen. That's good. Okay, so the homeworks, let me show you again. There's too many moving parts in this. So that, like, if you go to the web page, and then there's a homework here, and there's these 3 papers. Okay, so this is the homework, and it's basically dealing with this. Right, so that's my email. Right? That's what I was talking about. But say like Tuesday at midnight. It says here like January 16th is Sunday night, you know, but let's see if we can do it that they, I mean, for this one, Tuesday at midnight, say, but basically, so we can do it Sunday night and see if that's too much of a time crush for you guys. It's nice to be able to go through it right away, you know, and then we can kind of move on from the thing. Maybe I can get these out to you earlier, but the problem is I want to cover what we covered in class. So there's a little bit of a catch-22 in this thing. Let's see if we can do it. So anyway, this time it's Tuesday, so that should be enough time. Wait, so polymers, I mentioned last time that polymers crystallize in this with these chain folding. So you can have some dangling ends, and then this line's a polymer. And it's going to go in, and it's going to have this tightly knit folding, which might go on for a little while. This is looking at one layer, and then it might just go wander off again somewhere else. And then it could join another crystal somewhere. Right, so it could go into another crystal and then wander off some more. It could even like tie the crystals together. And so this kind of linkage, this tie chain would give the thing robustness. Right? It would be kind of looking at these would almost act like cross-link sites, and this would be like a rubber, like chains within a rubber. So you could think of those crystals almost like cross-link sites in a rubber. So it's going to give it solidity, but also give it some kind of flexibility. Right? So anyway, so there's a lot of different ways to look at it. So the first way, so the original way was to say, go back to thermodynamics. So the original way was this thermodynamic approach, like think about equilibrium. And last time I mentioned that if you have the alkanes, if you plot the melting temperature versus N would be the number of carbons in a carbon chain, which is going to be basically methyl groups like that, right? So N is like kind of how many carbons, and you'll get this kind of joggy thing at first, then it becomes continuous, and then it plateaus out when you get to about 100 units, right? And then you get a fixed melting temperature for the crystals. Once you get to this 100 unit transition point, you basically are forming this kind of crystal, this chain folded crystal versus crystals where the alkanes are lined up like that. So they tend to have this kind of jogging pattern when they're linear crystals. Anyway, so the question is like, why does that happen? You know, why does it go from that to that? And that isn't exactly answered, you know. So the equilibrium thermodynamics is basically coming from this Hoffman paper, Lorentz Hoffman theory, 1960, right, which is in here. So is this the same page? No, that's that book. Yeah. So we got these 3 papers. I already had them pulled up. Maybe I don't. Yes, I have. That's the class. So I can pull up the second one here. Oh, this isn't up to. This is the Hoffman. The Hoffman paper. It's a big file, I guess. I think it's just like a scan or something like that. There's a couple other papers here. Okay, so yeah, this is, you can see it's a scan because it's got like gray on the sides, right? So it's actually not a digital image. 1959. So this is the kind of the seminal paper for this, where this kind of chain folding comes from. And it's based on the Gibbs theory for crystallization, right? So there's something called the Gibbs-Thompson equation. And there's also this kind of idea of a nucleation event happening. It's still loading this thing. So this kind of plot, like you have the free energy over here, the Gibbs free energy, and then this is the number of units adding to the crystal. And there's a peak value for this. So when the Gibbs energy of crystallization, the change is a delta, it's a change in energy from the liquid to the crystal, goes negative, then the crystallization happens. Right, that negative change, a drop in the free energy, drives crystallization. And then when you're on this side, the crystals form spontaneously due to thermodynamic fluctuations, but they dissolve. Right, when you go on the left-hand side of the peak, when you're on the right-hand side of the peak, any growth of the crystal drops the free energy so that crystallization is driven, and this dramatically driven when the change is negative. Right, so there's a peak in this that's like the magic size for a crystal. If you get sizes larger than that, they grow. Smaller than that, they don't grow. So this is developed by Gibbs in Connecticut at Yale in probably like 1800s, late 1800s. Right. So, but Hoffman's applied this to this lamellar crystal. You see, he has another axis on the Gibbs would be the 2D, and Hoffman is this 3D with this kind of chain length that adds to the crystal face. So you have like the crystal face, then these chains are wandering around and they add to it. They add in. Right. But in the end, it's exactly the same as the Gibbs approach. And this curve is basically the Gibbs nucleation curve, and that's the critical nucleus size. So Hoffman's just taking this Gibbs, what's called the Gibbs-Thompson equation. Gibbs-Thompson equation, which is that the size of a nanocrystal is going to be some constant, some geometric constant, times the surface energy divided by the enthalpy of formation for the crystal, and then the temperature difference between an infinite crystal and where you crystallized, and then the infinite crystal temperature, all in Kelvin, right? Temperatures in Kelvin. So that gives you the size of a nano crystal that forms. Right, so that's from like, I think 1870, around there. And it's the Gibbs, Willard Gibbs. It's like the guy who invented Gibbs free energy. And it's kind of like the American father of thermodynamics. Anyway, so Hoffman took that, and then first he goes through a nucleation theory for the homogeneous nucleation, and then he goes to this. So this paper kind of goes through that. He ends up with homogeneous nucleation equation, which is 32 in here. You can see that they're wordy, like these guys are really wordy. So this is like the particle size. You can see that constant K from the Gibbs equation is 4 here for this homogeneous nucleation. And then the surface energy becomes this fold energy. Like, what's the energy to make this fold, which is a large energy. And last time I went through, you calculate the thickness that way. The 4 is different though. The 4 is for the initial nucleation. Once you get growing the crystal, okay, he comes up with exactly the same equation, which is like 104 here, someplace down. You can see these people are wordy. but they go through a lot of intimate details about what's going on here. This is slow to refresh because these are photographs of the pages, because this is such a 1960s, pretty old. 103, so 104 is the Gibbs Thompson, where that constant is 2 now. So the two reflects that this crystal has 2 surfaces. Okay, and so this is a number of pages that he went through, but to get that equation, you can just go, you can just say, well, I have a crystal, right? And it's got a volume, and it's got the transition, the delta H or delta G. So the change in free energy to form that crystal, that's this delta G that in Hoffman he's calling it delta psi, right? That's the energy to form the crystal, the bulk energy times the volume gives you the amount of energy. Right? So you can say like the Gibbs free energy, and then this delta G is going to be composed of an enthalpy and entropy. Right, so that's kind of like your basic Gibbs free energy. You can remember that if you want with the thermodynamic thermodynamic square. You can say they have G is H times, I mean, you read this like G is H and then minus ST. Let's go with thermodynamic square. So you can read like G is also the Helmholtz free energy minus PV. And then you can read all the others that way. And you can also get the derivative parts from this thing. Anyway, so forget about that. Anyway, so we have this equation for G. So you can say like, if you have G, you have this volumetric part. So you have like the volumetric and this delta G volume. But if you want to add in surfaces, and for this lamellar crystal, there's only these 2 surfaces. You're going to have this area, and you're going to have like the surface energy, the surface fold energy, and there's 2 surfaces because it's a sheet. And it's got that surface and that surface. So there's 2. 2 times the area times this surface energy, right? And this G, so if you have an infinite crystal, so if this thickness is infinite, then you have no surface is infinite. You just have this term, and if you set this delta G to 0 for the equilibrium, and this delta G for the volumetric term is volume times delta H minus T delta S, and you set that to 0 at equilibrium, so this becomes T infinity, the melting point. And then you can see the volume cancels out, and you just have the delta S is delta H over T infinity. And that kind of is the definition of this melting temperature. You can sub that back into this equation. So you can remove delta S. So delta H you can measure in a calorimeter, delta S you can't exactly measure. Right? So in order to get over that problem, you do this. You sub that in here, and then you end up with delta G. And so you sub in the delta S here, so you have volume times delta H times 1 minus the actual temperature you're crystallizing at over T infinity. And then you have this surface term for an actual crystal with a real thickness, right? So you have plus the area times the surface energy times 2, because there's 2 surfaces, right? And if you, so then you have like, this is a pseudo equilibrium, because you're equilibrating not an ideal crystal that's infinitely thick, but a real crystal. And in that case, you can solve for the thickness, because the volume by area is going to be the thickness of this crystal. No matter what the lateral geometry is, it will give you the thickness for the ratio of volume to area. So then you can rearrange this and say that the thickness, I mean, I can multiply, well, this is going to equal 0 at equilibrium. So then I have the actual melting point for crystal of this thickness at that temperature. And then that's going to give me the Gibbs-Thompson equation. And solve that, it would be 2 sigma E delta H of fusion, T infinity minus T infinity. Right, so it means that the deeper the quench I go to, the thinner the crystal. Right, you get thinner crystals for deeper quenches. So if I plot this 1 over the thickness at a temperature T, then this becomes a linear equation. And then it becomes delta H over 2 sigma E T infinity, which is a fixed number, times T infinity minus T. So 1 over T increases with, call this delta T, quench depth. How far you drop the temperature below the equilibrium temperature. So you could do a plot of this of 1 over T over delta T, and it's going to be like a line like that. And then when you get to delta T 0, then this basically is infinite. 1 is T would be infinity, delta T 0. Anyway, you get a plot like that, right? Yeah. So that's called the Hoffman or Gibbs-Thompson or the Hoffman-Lorentz equation, right? And it's in this paper. I gave you the original paper, but so you can see this is the real L. This is this critical nucleus L, the initial stage of growth from the homogeneous. And this will go on and on. So the idea is that the crystal, the crystal when it forms at this temperature, it has some defect. There's a surface is a kind of a defect. So if you want to plot, so if you can find the T infinity by plotting the temperature you crystallize at versus the temperature where it melts versus the temperature where it crystallizes at. And for an infinite crystal, that would be that's the line of equal Tm equals Tc. And for the real crystal, it crystallizes at a higher temperature. So you get this kind of, if you plot against different crystallization temperatures and then measure the melting temperature, you get points like that, and you can extrapolate experimentally to get the T infinity. This is called a Hoffman-Weeks plot. All right, so experimentally you can get T infinity, and once you have T infinity from the Hoffman-Weeks, you can plug it back into this Gibbs-Thompson and predict the relationship between where you crystallize it and how thick the crystal is. So this is all equilibrium or pseudo equilibrium. In other words, equilibrium would be an infinite crystal, and here this is an actual crystal, so we call it something like pseudo equilibrium or quasi equilibrium, which is a concept that was invented by Gibbs in the 1870s. And so quasi equilibrium to understand how things like surface energy can impact melting temperature. Right. So, and these aren't new ideas. And even in 1960, these weren't new ideas. So Hoffman took those things and put them into the context of polymer and came up with a pretty robust model that's basically the basis of how we understand polymer crystals today. Right. So Hoffman also was head of polymers at the National Bureau of Standards, which is now NIST, National Institute of Standards and Technology. It's kind of the NIH of science. And he was a pretty famous and boisterous kind of guy in his day, in the 60s. Right. So anyway, this paper is probably worth kind of looking at. And then, but there's this question about just do what I just did, like drive the Gibbs-Thompson equation. And then, so that's kind of the first thing about this. Then these other people are doing something different, right? So let's see what I got here.
Hey, Dr. Beaucage.
Yeah.
That equation, is that Gibbs energy on a per volume basis?
Yeah.
Volume
So
of the
you can,
crystal.
yeah, I mean, I was kind of loose here, but basically there's two Gibbs energies. This is the actual Gibbs energy of a thing, right? Usually, sometimes they call this, they underline this volumetric one, and this one's not underlined. I mean, it depends which book you look at. So this is per volume, and this is just the actual energy for the object, you know.
Okay.
And then
Yeah, I got.
in order to get this, you have to have an actual object.
Yeah.
So you have to have, and that way you get the volume and the area terms. And these numbers are what you look up in a table, like the per volume. So these would be volumetric numbers.
Mhm.
You have to look those up in a table.
Okay.
Or you can measure those if you weigh the sample and figure out how much per mass or per volume of the sample, you know.
Yeah, I got the Young and Level Intro to Polymers book here, and was
Okay.
following along in there, and it has it all volume based. That's why I was wanting to confirm.
Yeah. So you have this term is the, so these are what do they call it? Anyway, these are volumetric, and this is just for the actual object.
Yep.
So as the system changes, this number changes. Like you have a bigger system, a smaller system, that number changes. This number doesn't change, so it's per volume.
Hmm.
There's a word for that, but I can't remember it right now. Maybe you guys remember, but anyway, so there's two papers here. So that's like the basis of this stuff, right? I mean, that's kind of like, oops, that's one thing. I should have pulled these up before, but I didn't. So, you know, the course isn't really about polymer crystals. But basically, it's good to just pick up on something because these will have different aspects that I'm showing you real papers, you know, recent papers like this year or last year. And then like this is 2016 and this other paper is 2021, this one. Okay, over here, there. So 2016, Summer is a pretty famous simulation guy who was at Mainz in Germany, right? There's a big Polymer Institute there. And then moved to Dresden, which is in East Germany, right near Berlin. And then they formed like this Polymer Forschung means research, the Polymer Research Institute, Leibniz Institute. A truckload of money came, they piled it down. Summer left Mainz and went to Dresden. And then Potsdam is part of Berlin. That's like a suburb of Berlin where they have some national labs. Potsdam is where the peace treaty was signed for Churchill and all after the end of World War II. It's also right on the border with East Germany, so it's where the bridge is. There's a bridge where the spies were traded, you know, in the Cold War, where the spy would be like walk across a bridge. That's in Potsdam. And there's also a nuclear scattering facility there. Some other it's closed now because Germany shut down all their nuclear reactors. So, and then ETH is the top school in mainland Europe for science. It's like the Cambridge of Europe, of the mainland Europe. And then who's from there? This guy Kroger, I don't know who that is. Anyway, probably a student of Summer. But anyway, so they do molecular dynamics simulation. So the point is, like, we're going to go through a lot of this stuff, and some of it we won't, and some we will. But you'll see, like, that in order to read a paper, so say you're somehow interested in polymer crystals, in order to read this paper, you need to know like some bit about polymer physics, right? So I think the best way, since I can't cover every possible topic, you know, the best way is to just throw you into the pool and see if you can swim, right? So that's the concept here, right? So you're not gonna, this is gonna be kind of shocking, you know, the water might be cold, but basically the idea is like pull out as much as you can. So there's a lot of pieces in here in discussion that have to do with the basic concepts of polymers. The only way to really learn it all is to take, and the relevant things are the things that are being talked about today, you know, so that you don't really need to know everything about everything. You just need to know what people are talking about today and be able to piece it together, right? So maybe with the lecture and then with whatever you get, then you can piece together kind of what's going on. And I ask a few kind of questions about it, but basically doing molecular dynamic simulations, what you might probably don't know what it is, right? So basically you take your stuff, you're gonna basically beads, some kind of bead, and you say it's a molecule. If you want to do the original molecular dynamics, it's a molecule. It could be an atom, right? Then people got over that and they said, well, since you can only do like maybe a million atoms for the supercomputer, right? And the system I have has thousands of trillions of atoms in it to even look at something that's 100 nanometers, right? So this kind of idea of looking at single atoms isn't going to work because it's too many, and even there's no supercomputer that could do it, right? So it's basically you group up those. So you have like a bunch of those atoms. So you say, I'm going to deal with that grouping as if it's one thing. I kind of know what that grouping acts like. Well, what's the density of it? What's the energetics? Like what's the potential interactions between a grouping like that? And I can deal with groups. So that's called coarse screening. So then you get to CGMD. Everything's going to be acronym, right? So CGMD. So they're doing CGMD in this case. And generally, so even if you have atoms, you deal with some kind of potential that has this kind of attractive, local, and repulsive long distance potential between atoms. Say atoms approach each other. When they get close enough, they bond. If they're far apart, they repel. Right. So this kind of attractive and repulsive potential can be generalized to even this coarse grain. So this is like a 612 potential. We have like a local attraction, long distance repulsion. And you can get the numbers to match up with real materials. So you do experimental measurements, maybe X-ray scattering to see how things approach each other and what the distances are with temperature. And then you can get a 612 potential. They'll describe like what the energy of interaction is between two of these blobs. So somehow you get that, right? You can get some number for that. So then you have your system. Supposedly you start at time 0 or year 0 or whatever, and then you have your stuff, and the state you put it in is hopefully like random. So there's some question about, is it random or not? And then you're going to let these things subject them to temperature. So there's going to be some KT applied to it, and they'll have a velocity, velocity and acceleration, right? And then they're going to have a drag coefficient associated with it. So those things can all be done for whatever size scale you're looking at. You can put in equations for the dynamics, the drag coefficient, the damping factors of it. And then you let it evolve. So you're going to use this potential, like a 612 potential, or it could be more complicated. And you're going to use these random move it around with KT, and then you're going to let these dynamic kinetic parameters impact it, the drag coefficients, and it's going to evolve into something, whatever it's going to be, like a crystal, right? So there's going to be some kind of time when you reach T infinity. So you start with time 0 and T infinity. So you can't actually go to T infinity because you have a finite time you're going to sit at the computer, right? So basically you have to have some way of determining what T infinity is. So in this case, he's taken these beads, he's glued them together into a chain. He's made these like springs and dashpots to connect the beads together, right? And then he's got interaction energies between the different beads. He pumps all that information and then some kind of reasonable transport properties and puts that into a big black box, turns the key, and then just turns on the motor and lets it run. And it'll form these crystals. It'll form crystals, right? So this is time. So on his time scale, he can figure out he's doing actual steps. So he'll do like, I move this thing, then I calculate all the energies. I figure out if the free energy increased or decreased, and I accept it or reject it based on that. I want the free energy to decrease, right? So you do that for every so you have a million of these bead things, and you do that for all the beads over time. So with computers, you can do that. You can do a lot of calculations. So this is his evolution of the degree of crystallinity. So he starts with a 100% crystalline sample, and then he kind of lets it melt over time, right? As he lets things move around, and he says, well, I've reached a plateau here. I'm done, because I'm sick of waiting. This isn't really 3,000 nanoseconds. To him, this is like a month. Okay, so he's sick of it after a month. That's good enough. And then this is he can look at the coils, the chain coils, the size of the coils. So rate of gyration is one measure of the size of the coil. So there's two measures. So here, so he's got the chain. So that's what I mean by this stuff you don't know about, but basically it's got the chain as the end-to-end distance. So we had end-to-end distance squared goes with the number of units in the chain times the step length squared. That's that. And it turns out that the rate of gyration squared equals 6 times the end-to-end distance squared. The rate of gyration is something you can measure with scattering, like neutron scattering or X-ray scattering or light scattering. Right, so you can directly measure this rate of gyration. End-to-end distance you can't measure. So the idea is that you're going to take something you can measure and something you can't. You can calculate both of these from this computer simulation. So he takes the ratio, and a ratio of 6 would mean that these are Gaussian chains. So these are random chains. So he reaches a ratio. Originally, it's not exactly 6, and it kind of reaches 6. So he's happy with that. He says that's a sign of that he's reached T infinity. Then this thing kind of plateaus out. That's a sign that it's reached T infinity. So the game here with these simulations is, when is it over? Like, you never know when it's over. Okay, that's kind of an issue. And you can see when it's over might vary with the concentration of the system. So he's taken his polyvinyl alcohol. So he's got carbon, carbon, and then OH. That's the unit of the chain. And then he's taken a low molecular weight of that. I think like 4 of them. Right. So he's got a low molecular 1, and that's his solvent. So he has a solvent and he has a polymer. Right. And then he's going to change the concentration of the polymer and the solvent. The solvent and polymer are the same molecule. Right. So there's no real interaction between the things. At least that's theoretically. There's a lot of pitfalls to this, but anyway, so he's got concentration differences. This is pure polymer, the black one, and then he's got 66% polymer, or 69%, and he's got 50% polymer, right? And then you can see that the plateau here is different. So the degree of crystallinity changes with the concentration, and this is apparently consistent with literature. Right. He says that in literature, they also see a higher degree of crystallinity in the melt, which would be like phi is 1, than they see in a dilute solution. Okay, so, or this isn't dilute, but it's in a solution, like a 50% solution. And then the rate of gyration also varies with this concentration, which is suspect. Okay, this isn't exactly what you'd expect to see. You'd expect to see rate of gyration would be the same, but its ratio is always 6. So that means it's always Gaussian. So for whatever reason, as he decreases the concentration, his rate of gyration gets larger. Right? And he says he doesn't exactly explain that very well. Then this is something that he calculates 2 different ways. So this is the number of entanglements. So what he's interested in is the entanglements. So he has the chains, right? And they're going to form an entanglement. They're going to loop somehow, or some other kind of interaction. We don't know what that interaction is, but a loop is a common thing. And between those 2 loops, you have some molecular weight, Ne. Right. So as the concentration increases, so if I add another loop here, then Ne drops. Right. Ne drops if I have a higher concentration, which so here's his different concentrations. Black is the highest concentration, and he's got a small Ne. And you can see that for the black, it seems to equilibrate quickly, which is suspect, okay? Because this is the highest viscosity situation, right? So it should be the slowest equilibrating. And these other guys equilibrate faster when they're at lower concentration. Equilibrate slower when they're at lower concentration, which those should be lower viscosity, so they should equilibrate faster, right? So there's something kind of funny about this whole thing, but he doesn't mention that, right? He doesn't mention that in here. He's got two ways that he calculates this ME from his model, and they all plateau out. So he says I've reached T infinity here, so I can look at that last point here for my molecular dynamics simulation. I can say like what's going on with this thing, and what he finds out is that the number of entanglements drops with concentration, like you might expect. It follows some power law dependence. He says this is a linear plot, and he comes up with this power law. The power law is the blue curve line. Probably should have been a log-log plot. And then he finds out that that his crystalline thickness, this D, is linear in the number of entanglements, which and the numbers are kind of similar. So he says that this thing between the entanglements is the crystal thickness. That somehow becomes this crystal thickness. In other words, when the chains go out here to loop, they have an entanglement there. Right, and that's what governs the thickness of the crystal. So this is, all right, so Hoffman's theory was a thermodynamic theory, or a quasi-thermodynamic, but thermodynamic. He uses equilibrium to get the thickness, and it's verified by experiment. You can verify that easily by experiment. And this is a proposition. His experiment is this computer simulation, which relies on a lot of things like reaching T infinity is one of the main ones. And he's saying that it doesn't depend on temperature at all. It depends on these number of these entanglements. So this is a kinetic model. Okay, it's a kinetic model. So because these entanglements aren't real, right? The entanglements all have this tau associated. Remember, we looked at log viscosity versus log shear rate, and this shear rate is 1 over time. We found out that at long times, at low shear rate, you have a Newtonian viscosity, Newtonian plateau, then you can get this 0 shear rate viscosity. Then you find out that there's this tailover to a power law fluid behavior, and there's some tau associated with that. Right? So some time that it takes, that's the time that it takes a chain that's deformed in the shear to return back to like a random coil. That takes a certain amount of time, tau. Right? So if you don't give it that amount of time, it remains deformed, and the deformed chain has a lower viscosity than a non-deformed chain. Right? Partly because the non-deformed chains are entangled, and so they have a higher viscosity. This 0 shear rate viscosity follows the molecular weight with a power law that cuts off at the entanglement molecular weight. This is a slope of 1, so that 0 shear is proportional to the molecular weight when it's not entangled. And when it's entangled, this thing goes with molecular weight to the 3.4 power, about. Right? That's a squiggle, not a minus. So anyway, so that's kind of the story going on here. So these things have a time dependence. There's a lot of questions about a kinetic model, because what if you wait longer, right? Or how does this time dependence correspond in a thermodynamic crystallization process? Right? You'll see in the other paper this gets even more complicated, right? Because they don't have thermodynamic. This at least this thing, you have the beads attracting, and you have this 612 potential that says, yeah, they're going to attract each other and form a crystal. Right? You have this attractive potential that will make them form a crystal. In the other simulation, they don't have that attractive potential, but they still form crystals, which makes you wonder even more what's going on. Anyway, so there's this linear dependence, so that they're proportional to each other, means that this thickness is governed by this entanglements. Okay, so this is always going to be a question in polymers. Like you have kinetically dominated systems, and they have thermodynamic models. Because they're viscous, right? They're going to be dominated by kinetics, but you have these thermodynamic models that you're using. right? So this is kind of looking at, kind of introducing you to simulations a little bit, and then these are some pictures of how he crystallizes it. He mentions like Rouse dynamics and things which we'll talk about later on. You know, when he talks about how he does his simulation, we'll talk about why this end-to-end distance to RG is a factor of 6. So a lot of these things we'll talk about later, but you can kind of see that where things are going here. Like you need to have a whole package to understand any one thing, right? To get the whole package, it's better to look and see, well, I need some more information to really understand what they're talking about. So you get the information from the course, you know, but basically the best thing is just to let you try to swim and see how good you can fend for yourself with a few questions about this thing. So that's the idea. So it's basically like derive the Hoffman thing, and then something about entanglements. How do you get the entanglement molecular weight? So just what is he talking about with entanglements? And then this is about that other paper. Low is this paper. So this is how concentration affects. So I went through that before. So he's increasing the concentration, right? So what does that have to do with entanglement? So we had before the plot of log specific viscosity versus log of concentration, right? And that shows a similar to this. It's reminiscent, and for the same reason, of log of the melt viscosity versus molecular weight, which also has a linear slope, and this has a linear slope, and this goes to 3.4 slope, and this also goes to something like 3 slope. Okay, and this we said is the entanglement where molecular weight, where you can start to have entanglements where the chain can fold back on itself so that it can hook together. And this is a concentration of entanglements where you can start to see the chains are folding, but they aren't hooked together because they're dilute. And then at some point, they can start to entangle with higher concentration. Right? This is low concentration. This is high concentration, right, where they can start to entangle with each other. So you have this entanglement concentration. He's using this feature to talk about changing the entanglement concentration by changing the concentration. So this specific viscosity is this. It's the viscosity of the solution minus the viscosity of the solvent divided by the viscosity of the solvent. Okay, so it's kind of an odd thing. Like, why would you do that? The reason is, if you plotted just the viscosity of the solution, so if you plot like log of the viscosity of the solution versus concentration, there's a line where you reach the solvent viscosity, right? And that, yeah, you get a power law, steep slope 3, and then it'll reach the solvent and just go to the solvent because you don't have enough resolution. Like the solvent dominates it. So you need to subtract the solvent from the solution, and then you normalize by this solvent so that the scale has a 1 on it and a 0. So when it's 1, then your solution is 1 solvent viscosity above the solvent. Okay, the reason why you want 1 is because that happens to be exactly where this transition, or roughly where this transition to phi E is. So when your n specific equals 1, that's where you're at phi E, roughly. Okay, so you want to divide by the solution viscosity here, because then 1 has some meaning. It means the point where this entanglement thing happens. Right, and if you didn't do the subtraction to get the specific viscosity, you wouldn't see that transition because you just plateau out at the solvent viscosity. Because this is occurring at like 2 times the solvent viscosity. Where this thing equals 1, you're at 2 times the solvent viscosity. And that's where this entanglement stuff happens. Anyway, so that's kind of in here too. I think somewhere he mentions a specific viscosity in that paper. So I put that in too, so you can kind of figure that out. We'll talk about that later again, like we'll talk about that later on, but either him or the other paper talks about that. So the other papers, so you got a couple minutes. The other paper, this cost paper is one from 2021, right? So it's a different group. These guys are at Moscow, right? So they're like Russian, and then Holly, it's a school in Germany, right? And they're doing DPD simulations. DPD simulations is also a coarse grain, right? So it's called dissipated particle dynamics. So it doesn't have the 612 potential. It's got only a repulsive potential. So he gives the typical DPD thing here. So he's got this B is spring. So this is the beads of the chain, the bead spring constant. So the chain beads are springs. We'll talk about how that works. And then the C is terms of soft. This is a repulsion between the beads on the chain. So the beads on the chain have a repulsion and they have a spring, so they can dynamically spring back and forth. Then there's a dissipative, like a repulsive force. There's no attractive force in this. That's the point. The beads are glued together with a spring, but they're all dissipative forces. And then the last force is a random thermal force. That's going to be KT that will randomly move the beads. Right, so they're all simple. This is like a linear force, like everything's linear here. So it's all really simple equations, not physical, right? But nonetheless, this DPD approach can model macroscopic systems. So he's trying to model things on a micron or hundreds of micron scale. So you go to this DPD simple things where you don't have a 612 potential. It's just kind of make up a potential that you're using, and it may use absolutely the simplest potential you can do. So because he doesn't have attractive potential in this thing, you can't get crystals. So you can see what he gets. So you can't get really lamellar crystals. What he does is he has a solvent. So he has a solvent bead, and he has these chain beads. And he makes the repulsion between the chains smaller than the repulsion between the solvent and the chain. That means the chains are driven together to kind of phase separate. And then he tunes this bead spring strength to make these things straighten out into rods. And because they're forced together by this differences in the repulsive energy between the solvent and the chains, so chain repulsion and solvent chain repulsion, and the chain is weaker, so they're driven together, then they form something that looks like what you call a nematic liquid crystal. So it'd be like molecules that would line up in straight lines, and the transition would be that they would go random. So you have rod-like molecules that can go through this liquid crystal transition, and he calls that liquid crystal transition crystallization. And he ends up with these are pictures. The red are the crystals. You can see they're nematic liquid crystals because there's lines in them, right? You can see the stripes. And then he says that's a model for polymer crystallization. So this is a little bit wacky, you know. I mean, in the end, he gets, again, like you're going to have to let this thing run and like equilibrate. So you're going to have to find a point of equilibration that may or may not be true, and then you make some kind of assessment of the numbers that you get from it. So he's got, this is a simulation time. So it's the same kind of thing. You're looking for it to plateau out. He says it's plateaued here. Same thing with plotting, right? Degree of crystallinity as in the other paper. And then his crystalline size, so the size of these domains he forms, the number of crystals. So he tries to say it plateaus out at this 10 to the 8 steps, which is basically a month or whatever running this thing. And then the average crystal size versus concentration he gets here. So he gets this plot. So we got 1 minute. So this plot has 3 lines in it. So this is the distance between 2 points in the chain. So you can say, like, I have a chain of beads, right? And I have a distance between them, r squared. So according to our thing we went through in class, r squared should be nl squared. Okay, so then you'd have, this would be power 1 here. So r squared should be proportional to n if you have So he has proportional to n here, so that would be Gaussian chains. Right, and the other choice we had was ballistic. So in ballistic, r is proportional to n. So r squared goes with n squared. Ballistic meaning like a bullet, right? So it goes in a straight line. So this would be the case of his liquid crystals where they line up. And this is a case where it would be like a random walk. So you can see he has ballistic behavior here, and then he has 1/2 behavior, which would mean that r would go with n to the power 4. Right, so that's something that you need to kind of consider where that comes from. But anyway, so this plot's here. It's kind of interesting, and then he gets somewhat the same kind of result about the crystal thickness. Anyway, we're out of time here, so anyway, hopefully this will like give you guys something to do to look through this. There's questions about this that kind of this a little bit descriptive, and then a question mostly because it's a little bit. And there's 6 questions instead of 5, but I stuck one in at the end that I thought was important. So hopefully by Tuesday, you guys can get together with your teams. So the emails, like I sent out all the emails, I can send that out again to find out, so you can figure out, hopefully from the emails, you can figure out who your partner is. You know, like you can contact your partner. Send that again. This is, oh, send it work. Yeah, I'll send it out after class. I'll send you an email about any questions on this? So, oh, I get chats. I don't get chats, you know, I don't look at it. Let's see. In fact, I lost the chat here. You have to just say something. Let's see. Let's see where the chat went. Does each group have it? No, each group is either grad or undergrad. And then when will this recording be available on the course page? It would greatly help when working on the homework. Good point. So I'll try to get it up today. Like I'll put up the recording today. Actually, I'll just take the Zoom gives a, you can get it directly from Zoom. So I'll just send you the Zoom link and then I'll post it afterwards. So you can get the email addresses of everybody too. But if you have a question, can you just interrupt me? Like don't just send a chat thing because I don't look at that. Like I can't keep track of it. It doesn't matter if you interrupt. Okay. Any other questions? We're already over time, so. Okay, so have a good long weekend. See you guys later.